So those will be up. I apologize. Those will be up in a minute. I wasn't sure if I was going to carry my own system up here or not. This whole workshop for me has been deja vu. I don't know how many of you lived through the big data wave, and on that went to, with Hadoop and all these other frameworks, and that was very exciting. And the same questions were being asked then. I don't remember when versus big data when cloud showed up, but the two intersected very strongly. And then machine learning came on board, and it's just been a big ride ever since. So I know we were supposed to talk about some concrete future directions from material from what we talked about in the workshop, but I wanted to point out one area that didn't come up today. That's my slides coming up yet?
It's going to be in that it's not reading.
Oh, can I just plug right in, or? Yeah. Okay. Let's try that. Okay. It's on the HDMI input up here. Oh.
So it's happening at a technology conference.
Yeah, I can see it right there. So. Oh, thank you. Yeah, we didn't talk about, I saw under the 45 requirements, which, that we just saw from, your center, that you'd have to select very sparsely for any real solution, right? I mean, you're going to have to pick the 4 or 5 that you really care about, and it's not clear if they would overlap. Here's a good example of where there's a system that needs great velocity. We didn't really talk about that. Velocity could be throughput, but also we could talk about latency or delay. And when considering the cloud, it would have a big impact on a system where you're trying to do closed-loop neural feedback, maybe through fMRI in the case that we've been working on with Princeton. And you see if you go to the real-time neurofeedback conferences, it's becoming a real important thing in early clinical studies. For many disorders, from depression to schizophrenia, PTSD, and other potential therapies. But and you might want to use it just to visualize what's happening in real time as you're tuning experiment to brain activity to make sure you're activating what you want to activate, and that may require a bunch of pre-processing and analytics that you might want to do on the cloud. But also maybe other interesting work that's going on is the automatic selection of regions of interest within the brain using feature selection techniques at the voxel level, and that's something you want to be able to tune the hyperparameters of, like a machine learning model or some algorithm that you're using maybe for the selection and ranking of features. And then I mentioned the closed-loop neurofeedback. This is a really challenging thing to do with the cloud because of the fact that there's a network and you may have shared resources. You got to be really careful about the provisioning, but it's also a very powerful, compute paradigm to leverage for this, because you can trade off the number of machines for the latency and the computation. You can stage processing even across different regional data centers, if that will help. And so it offers all these benefits. You can, as I was mentioning, if you have an experiment, for example, if you want to do automatic region selection in the brain, it may involve an architecture that looks like that, which involves a number of machines and that can scale up to meet the service level required to return feedback between these regions, these times of repetition. So, I mean, it's good in that you can scale this unlimited processing, memory, unlimited storage and communications between the systems. It may or may not offload administration. We talked a lot about that today, who's responsible for what in these paradigms, and may or may not lower cost, and often it will, but it's hard for us to roll up our own, like brick and mortar cost numbers and look them in the face to realize that. And of course, and one of the most motivating factors for us in working with our collaborators has been to readily share tools, methods, and data to be able to do multi-institutional studies and to provide complex systems like that to researchers who don't want to get into that. Don't want to get into the computer engineering and the computer science for that kind of setup, which can work quite great for you and break through glass ceilings that you're going to face computationally. But the cost is you got to put it on the cloud, and because it's too hard to stand this up in everybody's private cloud or to create. It's not as simple as just creating a container environment. Now we're talking about a parallel distributed system and all the dependencies that it has. Okay. So, but the idea would be if you could do that and provide that to people, that they could do this type of neurofeedback. I love using that example because that's a really hard one. If you can do this type of thing, you could do full brain correlation analysis, for example, on one subject against maybe multi-subject data for other types of normalization over time and so on, and you can do that in under less than a second. You can do a lot of things. So, but the challenges are, that are unique to this cloud situation are the network and service delays. You've got to model the network. You've got to have some idea of what you're going to do if there are delays. It can mess up the entire research experiment or clinical therapy. You may not be able to recover from it. You have to develop completely different stream-based, in many cases, different stream-based pre-processing and analyses. I mean, there's relatively little work done on incremental machine learning algorithms. Some are naturally incremental, if you're using that. Types of filtration even, like the type of normalization you use, can't be forward and backward looking. You have to implement temporal filters. Everything has to be considered with stream-based processing in mind. And this is something, I mean, back to Russ Poldrak's discussion from this morning. I mean, BIDS and the Open fMRI and Open Neuro efforts have done a lot for figuring out and starting to deploy good standards for data and data repositories, the sharing of data, and even the running of analytics against that. Real-time brings a completely new set of challenges. You want to be able to describe the temporal data and the conditions under which that was done, collected, as well as the stream-based processing that maybe you've done on it, and what the requirements are for replicating that. So there's a lot of work to be done there, and I don't know of any efforts to describe data standards or processing standards for that at all. There is the problem of even being able to monitor such a system and being able to, going along with that, simulating. I think that there have been some calls in our breakout session on data management this morning for the need for validation of data sets, validation of the schema that you're using with data sets. Well, you also need to be able to validate that the pipeline is going to run with some probability as fast as you expect it to. You're going to be able to pull off the study with the locations involved and so on, and test that before you have much of it in place. And remember, there's this non-cloud component you have to deal with, some kind of data reaper or a file watcher, and the fMRI system itself that it's connected to, or whatever other instrumentation you're doing, using with it. And of course, And the cloud is only a good deal if you can get it for a good cost, if you can get what you need for a good cost. And we heard stories today about, and we've done this too, spending $30,000, $40,000 on some idle GPUs for a week or two, and getting nothing out of it. So if you want to be able to be elastic with this type of study, or to have it scale itself, you want it to run as fast as possible, but not use any more resources than necessary to pull that off. And that's a tall order. So, there is some progress. One good example I wanted to point out is this work that, Ken Norman and a student of his, Ann, at Princeton, along with UPenn, and some collaborators at Yale and University of Chicago are pulling this depression study through that is using a real-time cloud. We've got an analytics toolkit that plugs into that. It's all open source. This is a dashboard from it where you can see it. You can't really see it. We could talk about it later, where you can look at the activity that's happening in real time for monitoring, and you can look at the stages of processing that are happening and what subject and scan number you're on and so on. And so this is like one of the first uses we've seen of running the cloud in one area of the country and servicing an actual clinical study at a medical school in another. So we talked earlier, Princeton without its medical school, UPenn with this great collaboration is made possible through this cloud technology. And so far so good. It was not easy porting the local work, the workstation effort and all that to this, but it's paying off now, and we see many extensions that are within reach. So I think it'll help if we can educate the next generation of researchers to understand these tools and start using them in their research early on, and then maybe they'll be more willing to put them into clinical use and bring them into their research careers. So there's just as much effort around these things in putting them into classrooms and using parts of the cloud or the entire cloud in classes, in kind of 101 courses. And there's an effort at both Princeton and Yale where the toolkit used for this is actually used in the coursework now. I think there needs to be a bunch of other foundational work that's up to us, and the fundraising needed to do it for data standards, the hosting and reproducibility efforts to make it worth it. As well as advancements in cloud infrastructure. Now, there's a lot that Silicon Valley and the rest of the world has done to advance the infrastructure needed for this. A lot of them would say, well, geez, we can do stream processing like that today, but the domain, we can't underestimate the difficulty of the domain-specific adaptation and being able to communicate across those boundaries to really understand what is needed and what is possible with what's available. So I think that's, we don't have everybody in the room for that, but that's a discussion that should be ongoing for the next several years, at least. Okay, so that's what I got.
Can I just want to point to an aspect of this endeavor that we've been involved in with Intel that serves as a model, sort of a sociological model. Ted didn't emphasize it, he was too humble to, but that entire effort, which has been basically a 5-year effort, was funded entirely by Intel, and every bit of it is open source. There's not been one single moment where IP was an issue. It was at the beginning when we laid out the groundwork for the collaboration, but all of this was done with industry in an open source environment. I think that is a really good standard to hold the rest of the field to in academic industrial collaborations. And I think a real call out goes to Intel and Ted's effort within Intel to make that happen.
Thanks, John. You guys have been great too.